So good morning, everybody. First of all, on behalf of Oleg and myself, thanks for the invitation to speak here this morning. So I think by way of introduction, let me start off with, why is there a healthcare related talk, or why is there somebody from healthcare, and why us? So I do a couple things at Geisinger. One is I'm a clinical neurosurgeon, so I still practice medicine. I see patients, I operate on patients with brain and spine tumors. Number two is I'm our organization's chief data officer, which is primarily a strategic position for us that involves coordinating how we use our data resources and how we develop our infrastructure and our people to help extract the maximum value from our data. And Geisinger is a place that has a lot of data. We adopted an electronic medical record about 20 years ago now, so we're sitting on 20 years worth of EMR data, so we've had quite a bit of information, and it's always been part of Geisinger's culture to try to use that information, and so data is part of what we do and has been for a long time. And then number three is I head our data science department, which is largely an R&D type department, and that's primarily the hat that I'm wearing and that we're wearing today. Oleg Roderick is one of the data scientists in our department, and it's interesting because if you think about data science in healthcare, you probably think of it as a relatively immature field compared to a variety of other places. Doctors in particular are not well known for their statistical prowess and other such things, or ability to understand complex math. And so many healthcare data scientists are largely focused on fairly simple optimization problems, or essentially simple predictive analytics, that kind of thing. We're trying to take a different spin on that and look at some of the fundamental problems or fundamental challenges associated with data and with how we use it and how we make predictions from it and how we apply it, in our case, to the point of delivery of patient care. But really, our data science department takes some folks who came from anywhere but healthcare and brings their mathematical, computational, statistical, engineering skills to bear on some of the fundamental questions that allow us to do all of the things we do with healthcare data better. And so that's where we come from and why we're giving this talk today. And the topic is something that's of particular interest to me and to our group, and has been for a while, which is the whole idea of dirty data and what it is and how we use it, and can it be used, and to what extent, and how do we know. So just by way of disclosure, because of course we're an academic, I do some consulting. If you Google me, you'll see that. This has nothing to do with that. This is a Geisinger talk, so that's fine. I only have one Twitter handle though, so if you feel so inclined as to live tweet this because it's so amazing at 9 o'clock in the morning, there you go, you can use that one. So, healthcare. What's interesting about healthcare and data, and why it's a good place to do this kind of work, is that we have a lot of different kinds of information. So there are a lot of sectors that deal with bigger data sets than we have. There are a lot of people with terabytes and terabytes of sensor data and other such things. But healthcare's got circumscribed amounts of many different kinds of information, and it comes from a very practical setting. We get it from patients, we get it from patient-reported data, we get it from lots of imperfect measures of collecting things, we get it filtered through the eyes of doctors and nurses, and so it also happens to be noisy data, dirty data, skewed data. Basically, any way you can screw up a data set, we've managed to find a way to do it in healthcare, right? And that's good because it's a great place to learn how to deal with data that has those problems. And so I think we have a real opportunity in the area of data-related challenges to be leaders in the space of what we do with these things. So we asked the fundamental question, what is dirty data? And I think everybody has heard someone say in a relatively fickle fashion, well, garbage in, garbage out, and so if you don't have high quality data, you're not going to have high quality results. And of course, I agree with that. You can't make good predictions off of bad numbers. The problem is, how good are we at recognizing what are bad numbers and what is really dirty data, and what data prohibits us from drawing certain conclusions, and what data may have problems in the data set but doesn't actually prohibit us from asking the kind of question or answering the kind of question that we want to answer. So we think about, where does this dirty data come from? Well, like I said, we have it filtered through lots of different eyes, lots of different systems, and so we've got a lot of opportunities for looking at skewed data and data that has noise-related problems, a low signal-to-noise ratio, missing data, sparse data, rare events type predictions, right? This is the world that we live in. And why do we care? It's because in healthcare, as in many fields, it's relatively expensive to get the data in terms of the resources that are consumed to extract it from patients, the doctor's time, the nurse's time, the diagnostic modalities, the patients have to come in, this sort of thing. It's not easy to gather. And so we want to make sure that we're making the most out of the information that we have. And I think to just say, well, garbage in, garbage out, this data set is sparse, I can't do anything with it, and throw it away, oftentimes takes a potentially valuable data set and a potentially valuable data resource and causes us to summarily dismiss it when that's really not necessary and in fact relatively imprudent. But the question, of course, is trying to decide what do we do with that data that, when you take a superficial look at it, looks dirty, right? So do we try to clean it? Do we spend a lot of time filling in the gaps? Do we spend a lot of time looking for erroneous results and tweaking them just a little bit to make sure that those numbers are spot on correct? Certainly I know people who argue that this is the thing to do, and I've worked with some folks who have taken this to the extreme, to the extent where they almost can't sit down or won't sit down and try to write a predictive algorithm until they're 100% certain that every cell, every field, every table is complete, is thorough, is accurate, and then they move on to the next phase. The problem is sometimes it takes them years to get to the point where they're willing to move on to the next phase, and that's not so helpful either. So I tend to take perhaps the extreme opposite view, which is to say, let's start with the information that we have and let's try to learn what we can ask reliably about it. And if we understand what we can ask and what we can't, and in what ways the errors that we find in this specific data set affect the kind of questions that we're asking downstream, as long as we know what to expect, we can say with some degree of certainty, yes, this is the kind of question that I can ask of this data set and still get a reasonable answer, even though there's error in it, or no, this is not the kind of question I can ask of this because it's just so flawed in a way that is so important to asking the question that we can't trust what comes out, or this is a data set that's pretty close, and if I make a small investment of time and effort in cleaning focal things about it, the quality of my answer will get much better. So I think to just say, oh, it's dirty data, forget about it, garbage in, garbage out, dismisses an awful lot of the potential that we have with a lot of real-world data. Now, of course, the question is, how do we know what's the difference, and how do we figure out those pieces in the middle? And so I think sometimes it's reasonable to accept it, and I think the question, of course, is figuring out how. So at this point, I'm going to turn it over to Oleg Roderick, who's my lead data scientist in our group, and he's going to talk a little bit more about the nuts and bolts of how we've chosen to approach this question and some ways that we're thinking about studying the consequences of what we call the consequences of decisions about data. So by looking at a data set, understanding the kind of error that it has, and then perturbing it in certain ways and looking at how certain things change, trying to get a sense of what kind of questions we can reliably answer and what kind of questions we can't, and how much those little changes that we might make in the data set can improve the quality of our prediction. So my job is to frame the question and then to turn it over to somebody who's way better at math than I am to tell you how we actually answer the question. And so with that, Dr. Roderick.
So do I need to do anything to turn this on? No? Excellent. So thank you all for being here. Let me say a few words and show you about 10 pictures. The tone of the conversation is going to change a little bit because I have way more arrows, and but I'm trying to be a little bit more specific. So as Nick has already said, we're dealing with data that comes from multiple sources of very different size and integrity. This is a picture that I'm not particularly proud of because it's very approximate, but it gives you an idea that some information we know about our patients in extreme detail, and we know for almost 100%. Like, we know what everybody is called, we know what everybody's ages are. At the same time, the lab results, somebody might not have a lot of lab results, somebody might not have results reported in a particular way that we're interested in the database. So we have at least 9 different sources of information that come with different levels of integrity. That is a lot of variety that stuns and confuses people. On the other hand, the analytics protocol is fairly straightforward. We have a person with the medical information. In the 21st century, as they're walking into the hospital, before the doctor even gets to see them, we should, in principle, already know the likelihood of different events happening to them. What are the risks? What are the resource allocations? Do we need to allocate particular medical personnel time? then we need to turn on expensive equipment. Fortunately for us as humans, people don't have complicated medical histories. We don't have a patient that had 10 different kinds of heart attacks, so we cannot extrapolate from the past history of a patient. We need to connect it with other people's information. That is extremely diverse, extremely damaged, but fortunately for us, high-dimensional. We take individual patient's history, we relate it to clinical history for a population of patients. That first arrow there is where all the damage is actually hidden. Because once we have pulled data and aggregated it as a training data, we're accepting it as gospel truth. And if a bad result comes out, well, you can blame theoretically that somebody who did something wrong in the beginning. We suggest to move one step further and attach that blame quantitatively and do something about that blame. In an ideal situation, everybody who wants to do a data-driven study in healthcare should have some sort of a process of ingesting data into the model. We decided to give the task to the first-year computer science student because we wanted to keep it very straightforward and simple. And so we worked with him for a couple of weeks. And then now we're giving that task to slightly more advanced people. But the idea is very straightforward. If you read data, find out for every item of data what it is. We wrote a set of simple scripts that read numbers. If they're numbers, they're keeping them as numbers. If they're damaged, missing entries, they're using imputation techniques. Now, this is the important part. Every time an imputation technique is called, we record the reliability of that imputation technique. So that in the end, when we have a fixed table with no gaps in it, we will have another table next to it, identifying which data is actually real and which data was recovered, and assign different levels of fidelity. How to assign levels of fidelity, that is another question. What's important in this talk is that now we have a placeholder for the importance of every particular data point. And keep going. If it's not numerical data at all, we need to convert it somehow. Need to have a conversion process. The simplest conversion process is build a dictionary. You know, Monday is equal to 1, Tuesday is equal to 2. Who said that this is the best assignment of numbers? No one did. I am trying to bring this up to the following conclusion. Both damage in the data and operations you perform on data in the normal course of preparation change it somehow. You can in fact damage data in an attempt to interpret it and fix it. Let's treat all the operations made on data as the same kind of operation. We are not really fixing data, we are not really damaging data, we're just changing it. And let's trace the consequences of those changes. Developing that same idea, what if the data is not numeric or symbolic at all? What if it's images or a narrative written by a doctor that would typically be a PDF file with some keywords in it? Or real-time vitals data, you know, at resolution of 10 times per second. Nobody is plugging that into a statistical model. They should have some intermediate step, some sort of external tool that converts dense data source to numbers. Record reliability of that conversion and propagate the reliability throughout your whole model. And in the next picture, I'm trying to see in principle how it would be done. On the right, in blue and gray, you have the process as it's happening right now. Raw data is becoming transformed data. It gets put in the statistical technique. We have analysis results. On the left, in green, we have something that needs to be built on top of that. And the elements of that are take the data in the transformation, take all your dictionaries and all your notes of reliability, on reliability. A note on reliability is essentially a measure of variation of this particular data point. You think there is number 5 written there, but it's actually plus minus 2. So treat that as a stochastic variable and use either an analytic or a sampling technique. Make all the plausible changes to data that you can afford. Our computers are pretty big right now, and unlike humans, computers don't get bored. You can ask a computer to run 10 to the 6 hypothetical scenarios of what else your data could be. The trade-off here is that we cannot afford to have a very complicated predictive model. That thing in the lower right corner, that could be a fairly sophisticated adaptive technique, maybe with some human decision made in the middle. We cannot automatize that, so we don't. Instead, we have a simplified predictive model that serves as a placeholder. It could be something as simple as a linear regression model. We don't know what you as an analyst want to do with your data, so we're not going to guess. We're going to do something very, very basic. Put your data through a linear regression model and see how damage in your data influences the output. Make it more complicated. Put it through some sort of transformed linear regression model, logistic regression. Find out what is happening in the output. In the very end, you will have some analysis results versus hypothetical analysis results due to damage in the data and attempts to fix it. You compare the two measures of variation. If you like the variation, if it's small enough, don't clean the data, it's good enough. If you make tiny little changes to data and the results of hypothetical analysis are becoming hugely varied, that data is maybe not extremely important, but it is extremely sensitive. You need to make efforts to fix it. Thus, for the first time, at least in healthcare field, we have a quantitative approach to figuring out how to prioritize efforts in cleaning the data. This is an idea in process, it's not completely finished. Now, if you read literature on cleaning data, you will see that people are obviously getting paid per page. There are taxonomies of damage done to data that run into 200-300s. Especially with financial data, there are so many different ways in which a payment could be reported wrong. And I get why they need it. But we're going in the other direction. We're trying to simplify it extremely. This is our simplest taxonomy, and if we can cross out one part, we will gladly do that. Those are all the different 5 things that can happen to data represented in the table. Transformation, you remove a feature, you add additional data, you remove additional data, you recover missing entries, and then you just introduce numerical perturbation. That could be due to you trying to fix the data, or it could be present in the data already. Number 6 is a little bit unusual. This is our first step in moving from the tabular format to actual relational databases. That's when a relational link is established in the data. A simple example would be, suppose you have 4 entries, you want them to always add up to 100%. People who use Excel to engineering calculation should be very comfortable with that kind of thing. That is also a deterministic thing that happens in the data. With the help of that, you could start asking very unusual questions. For example, we run a study on our population of 3 million patients. We come to some conclusions. As about 30 to 50% of publications in medicine, it's very hard to reproduce because we will never show you our data. We will not show you all of it. There is no reason for us to. So we can ask the following question. How can somebody reproduce the results of our study without having access to our full data? Well, don't give them our full data. Scramble the data. Make some features anonymized, remove some features, and use some features as placeholders for other features. Like, we are not giving you the actual physical addresses of our patients, but we could tell you how far away they live from each other, abstractly. That is a set of basic operations. We can actually, with the help of the tool we propose to develop, answer formally the following question. What is the maximal damage done to the outcome of your study, given that you have performed this anonymization on the data? From the point of view of the user, we were thinking of a user interface, and we rejected that idea. There is no reason to have a pretty picture on the screen, because the data will probably be too big and too complex to fit on the same screen. So right now, what we're considering is some sort of a query language that will allow the user some conditional statements, so he could fill out that additional matrix I was talking about in my first slide. Next to the data, you will have a map of supposed reliability of your data. And then the user will answer simple questions, like what parts of the data are compromised or suspected to be compromised, and what are the allowable operations we do to fix the data. And then we do one of the 2 things. Either we just do those operations, do 1 million of them, or 10 million, however much we can actually budget it to the computational power available. If you're not happy with that, and that's a very appropriate slide to have at Wolfram Data Summit, we need our system to act as a computer algebra system. Allocate variables for training data, training data labels, parameters, testing data labels, error, and projected results due to damage in the data. And just propagate the damage in the data through all the deterministic steps. It might not be pretty, but mathematical tools are completely prepared for that. People already do it in engineering calculations that are fairly simple. Let's do it in our more abstract, vague data science calculations. This is a fish, because we decided that abbreviation of consequences of decisions made on data should have an angry fish in it, called meta. That's what we have instead of sense of humor. I'm sorry about that. Truly, I am. It is a work in progress. Right now, we have a set of Python libraries onto which we are going to be adding features all through the next year. What it can do right now is take your data, take your matrix of flags, that will identify that data is unreliable or completely missing and do different types of imputations, for example. We have a few basic operations like that. We are not up to fully integrating everything I listed in taxonomy, but we are close enough. The output is a little bit not user-friendly at the moment, because as I said, an output is really a cloud of points. It's a cloud of hypothetical outputs of your study. Now, an output of your study is by itself not a single point. So we could have 10 to the 6 state vectors that are themselves maybe 10 to the 4. How do you report that to the user? We're not quite sure. So I'm going to very quickly and show you some pictures with clouds of points. The idea being that in development, we will decide what measures of variations are important. But what to do with them is pretty straightforward. If the variation is small, you accept it. This is a picture that's comparing 3 different ways of imputing data. The one that has the tightest lines, you accept it. That's the one that has the closest bars to each other. That's effective imputation on classification. That's effective choice of imputation methods. That's on a very big data set. That's a few gigabytes of data actually leading to that output. Effects of missing data. Here is a more realistic experiment. That's something we would like to do much more so of in the future. You essentially ask the user if they like the resulting variations in the data. If the picture on the upper left corner is acceptable to them, they could have 10% of their data missing. And this is sampled over data uniformly. So in this particular study, they could safely have any 10% of their data missing. On the other hand, the picture in the lower right shows huge variation, and all the structure is already obscured. So maybe you don't want 30% of the data missing. I hope that I asked more questions than I answered, because this was fully my intention. I hope that I will be able to have some productive discussion afterwards with people making remarks about what is missing and what needs to be done. Main points, just in one long sentence. Interesting data sets will not ever be made entirely clean, because there is such thing as unknown unknowns. You think your data is cleaned up, but it's actually damaged. But you could hypothetically examine the effects of your data being damaged. We suggest developing a hybrid sample analytic tool that traces consequences of operations on data to outcome of the study and allows the user to make decisions in a more informed manner. So that was my part. Thank you very much for your patience.
So I'll take the last 1 minute here to just summarize. So the way that Oleg and I give this talk is I kind of start by presenting it in English, and then Oleg presents it in math to prove that there's some legitimacy to it for the people who really like the mathematical side of things. And then at the end, I try to bring it back to English that somebody like a doctor can understand. So I think the point that we're trying to make with this is, number one, we're really thinking about changing the fundamental way that we look at a set of data, a set of features, because it's not just about looking at them as a series of measurements or as a series of points that you can use to predict or describe something. It's about looking at each one of those as an approximation with some degree of error associated with it. And intrinsically that makes sense, except data scientists in general, and certainly in healthcare, don't often approach data like that from the very base level of modeling, right? And so this is why I actually hunted up somebody like Oleg, who's got mathematical experience, particularly in uncertainty quantification, because I think it's important to not just make a prediction and not just build a model, but to trace the consequences of the uncertainty of each of those variables throughout the process. And I think this is really our effort to understand that at the very beginning of the entire process, so that we can say right away when someone hands you a set of data, can I answer my question from this or not reasonably? And I think that's a very simple question, but it's something that we don't always have our brain wrapped around when we're starting a data science project or a predictive analytics project. And so what we tried to do was go from that basic question via a series of uncertainty quantification steps to come up with some way that we could say at the very beginning of a project, yes, you can use this, no, you can't, or yes, you could use this with a little bit of a twist on it, or a little bit of cleaning, or a little bit of adjusting. And this is our answer to that. So like Oleg said, I think we've got it to the point over the course of the last year where it's a pretty mature idea and we have a pretty mature approach to how we're dealing with it. And now we just have to catch up with the coding. And so it's, it's not a nicely polished, finished graphical user interface. And I said, Oleg, can we make it look nice? Can you make a pretty picture? Can you turn those clouds into something three-dimensional? To which the answer was, you don't even understand what we're doing, obviously, if you can ask a question like that. So the point is, it's hard to make a pretty picture of this, but when you really start to understand the variability of the data set underneath it, you start to see and start to think in these kind of clouds. And it reminds me of 8 or 10 years ago when I was doing computational biology and genomics work. There were whole families of plots that were introduced that people looked at and said, what the heck is that? But after looking at them over and over again, they described the uncertainty of microarray microarray measurements and such, and it became part of what we do. So we're starting to think like this, and we're starting to think more in probability clouds and less in discrete points, and we're carrying that thinking all the way through from the beginning to the end. And I think at the end of the day, what that allows us to do is really understand our data better from the beginning, so that we really understand when we get an answer, how sure are we that that answer is the right thing to do? But also, when we get a set of data, how sure are we that we should be spending our time even using that data to answer the question? And how can we wrap some numbers around that? And how can we measure that and not just sort of have a gut feeling about it? So these are the kind of fundamental questions that interest us, and this is one way that we're approaching that. And hopefully next year at this time, we'll have something that at least has some sort of pretty pictures that we can show you and a more robust user interface. But in the meantime, we're happy to talk about anything from the application side of this to the very detailed computational side of things, and we welcome anybody's input. So thanks, and if you've got any questions, we've probably got a minute or two, and then we can connect afterwards.